Are you going to continue doing projects after this one?
Yeah, I guess. Well, I want to avoid getting in trouble or even having to deal with the conversation. I just do it and move on.
Getting in trouble from whom? Cal?
I mean, yeah.
Okay.
Try to avoid that. As of right now, I'm teaching calculus next semester, so hopefully I won't be wrong. I think Jennifer is doing exams.
Yeah, but using the proper view, which I have feelings about.
Yeah, I don't know anything about that.
What?
I don't know anything about that. Yeah. It's all hard.
Yeah.
Is it like annoying to do it?
Oh, I don't use it. I mean, I'm teaching 2200, right? The next semester. I think I'm teaching. It's been nice not having a supervisor to run everything through.
Get onto the home stretch here. So are most people staying around for full break or? Yes. Okay. Yeah, so today I learned that Jim Humphreys passed away. I'm sure you've all sort of been influenced by Humphreys in one way or another. He passed away on August 27th. And his obituary is actually online. It was from so I thought that it would be appropriate since a lot of the work that he did was very seminal to the development of the subject that we're actually studying in this class, that we all stand for a moment of silence. So if you would please stand, just take a moment of silence. Okay, thank you. All right, so today what we'll do is we'll start by actually looking at what are called facets and alcoves, because I don't want to keep on using these terms without defining them kind of precise way. So let's take a little time now to learn about facets. That's watching the French and everything. All right. So the idea is that if you take the outlines to values, this acts on the Euclidean space, which is M sub P, tensor Z, R, these external scalars, by the dot action. Okay. And when you do this, what we want to do is we're going to be able to describe certain alcove geometry. So let me draw you a picture. I'll try to draw a new one, E2, maybe sometime this lecture. Okay, so here's our typical A2 picture over here. And so here's what happens under the affine vial group, and it keeps on going. Okay. All right. So the idea is that you take a subset of roots, say positive roots, and you sort of divide things up. So I want to divide the positive roots in a disjoint union of what I'm going to call phi 0 plus union phi 1 plus. And this is not super algebra, it's just, just dividing the set up into two. And the phi 0 plus will sort of be the roots which are kind of on walls. So the weights which are on walls. Okay, so F, we're going to define this to be set of all lambda. So lambda is actually in this set of the Euclidean space. Such that lambda plus rho alpha check, this is equal to n alpha p for alpha in phi 0 plus. I'll just ignore it with the F for now. So basically, for this subset phi 0 plus, you actually are on a wall. Okay. Now this multiple n alpha depends on alpha. Okay. Now, for the things which are not on the walls, I want them less than or equal to things. So I have that and n alpha minus 1 less than or equal to lambda plus 12 alpha check to be less than n alpha. And this is for all alpha, which are at phi 1. Okay. So this is called a class. And so, you could have, you could have various positions, right? You could have your lambda be here, right? And then in that case, this condition wouldn't hold, right? So you'd have this condition only holding. So phi 0 plus is the empty set, okay? On the other hand, if you have something like right here, say this lambda, then this would line up for the root alpha plus beta, but you'd have this condition being true. Okay. And similarly for these walls, and also for any of these vertices. In these vertices, these are all multiples of p. So then this condition. All right. So does that make sense? Question on this? All right. Okay, so now I want to define what's called the upper closure. And so the idea here, let me just say what the closure is first. So I'm going to say what the closure is. Okay, so as you can imagine, if I take this kind of set here, let me call this something. Okay, so let me erase this right now and redo this. So this CZ bar, CZ can be a facet, right? So for example, F could be equal to just CZ. And that would just be the interior part inside of here. Okay, so you would have just this condition being true. Right? For things on the interior of this. Now, if I want to take the closure, I want to include all these walls too, right? So in order to include the closure, I have to put less than or equal signs here. Okay. So the closure of the facet, this one in particular, is just lambda plus rho alpha check equal to n alpha p alpha and phi 0 plus and lambda plus rho alpha check less than or equal to np alpha p bigger than or equal to n minus p. Okay, so I'm putting the less than or equal signs here, and that's all alpha and phi 1.
I'm saying what of the two conditions correspond to?
It corresponds to including all these walls, or including the walls.
That's the inequality?
Yeah.
Or- okay. And what is the first condition? Just being equal to alpha?
That would be like, for example, if you're already here, yeah, then you don't have to worry. The closure as a whole is going to just include the endpoints over here again. So these are. Yeah, so think of the F as being sort of like the open part, and then the F bar to be the closed part.
So the spots where the inner product is just equal to an alpha p, is that like are those the vertices in that diagram? Or
Yeah, when they're all when this is equal to n alpha p for all phi plus, those are the vertices. Yeah, exactly. Good. And then we have this notion of upper closure. So we're going to use this later on. And so, so in this case, what we do is we just make this thing to be less than or equal to. I'll just write it out. So time to absorb this. And then the other equation is this, where we still make this strictly less than. This is called the upper closure. All right, so let me do a few examples.
There's supposed to be a phi somewhere with the n alpha minus
Yeah,
1.
yeah, there should be a few here. Sorry. Okay. All right, good. So let's do this example here. Let's see. I can erase this part.
The only difference there is you just change just one of inequalities.
Yes. Yeah, you're just looking at this one. So if you want to look at, let's just do this one over here. So let's just do CZ bar hat. Okay. So CZ bar, when I take this thing over here, then it turns out to be, let me make sure. Yeah, so I think the upper closure is just this wall up here included. So if I take CZ hat, then what I get just the upper here, turns out. Right. According to my diagram. The whole closure includes these two walls. Okay, so a facet is called an alcove, if and only if, let's see, phi 0 plus enough is equal to the empty set. So basically, your lambda can't lie on any other walls. Okay, so an alcove will just be like the interior over here, CZ without the bar. So, and there's a fact that we're always going to use. So if F is an alcove for the action of WP, then closure is a fundamental domain. Or WP. By the dot action. So what that means is that if I take a weight up here or anywhere on here, then I can take this alcove, let's say down here, and its closure, and I can keep on flipping all the way, and I can get a W orbit of this thing that includes this weight up here. Okay, so I can reach any weight by just, taking certain affine valve reflections. Okay. And also, this action is transitive too on alcoves. So you can get from any alcove to another alcove by using the action of the affine valve. Okay, any questions on this? All right. Now, I want to go back to the definition of the translation functor, and then we want to prove the adjointness properties for the translation. So let's do that. Let's just erase this for now. So let's go back to the translation functors. All right, so recall the setup. So I take lambda mu, and let's say they're in CZ bar. Okay. So I'm going to define a functor which goes from, sorry, it's the other way around, the lambda block to the mu block. Okay. So I'm translating from lambda to mu. And the idea is, first of all, I want to take PR of lambda. So I'm going to take the lambda block of my module, and then I'm going to tensor it by a certain irreducible representation. And this dominant weight by taking the W conjugate of lambda minus mu. Okay, we can always, if you take the difference, you could always conjugate it into the dominant chamber under the ordinary action. Good. So that gets this, and then finally, I'm just going to take the mu block of this. All right, and so what did we show, or we just indicated? We indicated that this functor is an exact functor. Okay, it's exact because when you project, that's an exact functor. When you take the tensor product, it's an exact functor. And then if you take another projection, it's exact. It's a composition of 3 exact columns. Okay, good.
Why is the tensor product back here?
Because I'm taking a tensor product over the field. Right. And yeah, over arbitrary rings that may not be exact. Or field rings. Very good. All right, so here is the lemma. Okay, so this is the lemma. Let lambda mu be weights and m finite dimensional G mod. Okay. So the functors. Okay, so I have to list these functors. So they're basically going to be things which look like this. So F blank, which is PR mu, composed with M per blank, composed with PRM. Okay, so basically I just take PR of this module, I take the tensor product with M, okay, and then I take PR of this whole thing. Okay. So basically it's just this over here, except I'm just replacing things by. Okay, so G is going to be the following. So I'm going to take PR lambda, and then I'm going to take the dual of M. And I'm going to take blank, I'm going to take PR again. So the lemma says that these two functors are adjoint. Adjoint. Okay. So let me remind you what this means. It basically means if I take HOM over, let's say, this category C, C is just a category G modules. G blank, so I have A. This is HOM of D, so this category D. And then you can just kind of move the G over the other side as long as you compensate by that. And vice versa too. So HOM of D of blank GA. F of blank. Yeah, so G is a functor from D to C, and F is a functor from C to D. Actually, no, I guess it's the same thing. Make sure I got these right here. I probably got them mixed up. Let's see. I think this should be a C and this should be D. Otherwise, it's kind of saying the same thing. You can see F. So let's just look at this for a second. So G should be a functor from where to where. So it should take things in blank, so from D to C, right? And F should be a functor which takes things in from C to D. Okay, does that make sense? All right. Okay, so let's see over here. So F is a functor which takes things from C to D. So this should be a D down here.
I think I can see on the left.
Yeah,
and the right.
yeah, I think it's okay. Right. Okay, just making sure. Okay, so this is just a computation. It's a computation using HOMS, obviously. So let's just prove this. Okay, so let's put in actual modules. So let V and V prime be G modules. Okay. All right, so let's look at HOM G, F of V prime. Okay, so let's write that out. So this is HOM G. Okay, what is that? It's PR mu M tensor PR lambda V, right? V prime. I'm just using the definition of F. All right. Now remember that when you're in a block, you're only going this module here is in the BR block, mu block, right? So it's only going to talk to things over here which are in mu, right? So the components in mu. So basically, I could just kind of switch this to the other side. So this is going to be HOM G M tensor PR lambda V PR mu. So the only homomorphisms that are going to talk to each other are the ones where you just pick out things in mu, which are linked to mu. Okay, good. So now what I do is I move this tensor product to the other side. I can do that by taking a dual. Okay. And now by the same argument, this will only talk to the components which are in lambda, right? In the block of lambda. So this is HOM G V PR lambda and star tensor PR mu prime. Okay? Which is precisely what G is. Too many G's, but I think you can understand from context what I mean. So this is another G, okay? Not the same G's. So this shows adjointness. And then you could do the other one, just with a similar argument. Okay. So other conditions.
Quick question, maybe
Yeah.
going from the third line to the fourth. Why can you take the projection of lambda off of the left-hand side?
Oh, because the thing is, the only component that's going to actually talk with this one is PR lambda. So in some ways what you're doing is I could just say HOM from PR this thing to PR that thing.
Yeah.
Right. And then I could just take it off that.
I see, okay.
I mean, that's kind of, you have to kind of think through it. It's kind of neat how it works. A lot of times in representation theory, what you want to do is you kind of want to throw out extraneous stuff. And you can do that using these homological invariants because, like if you have a block, a module, category in a certain block, then it can only talk to other modules in that block. With the other modules, the extensions are all zero and, the HOMs are all zero. So in terms of cohomology, you don't have to really worry about that issue. Okay, good. All right, so now what we can do is we can show that these translation functors, when I take T lambda mu, it's adjoint to T mu lambda. So that's our next result. And this adjointness is quite important because it allows us to be able to do computations by moving the functors to the other side of the Hom. So I don't know if you ever do this in math, but I really hate to use like lemma corollary. But you think that a corollary shouldn't follow from a lemma. Let me just state this as a theorem. It's sort of bad form, I think. Maybe people will correct this. So let lambda mu. Suppose that's in the closure of the bottom alcove. So then, when I take T of lambda mu and T of mu lambda, these are adjoints. Okay, so proof. So if you use the previous theorem, if you take P mu L nu 1 tensor P lambda length, this is adjoint to when I just interchange these two, PR lambda L 1 star tensor what? Tensor P on U. Okay. So what I have to do is, I know this one is T lambda mu. And the question is this T mu lambda one? Right. So the question here is this T mu lambda one? Okay. So what I have to do is I have to show, so who can tell me what I need to prove?
You got this L in self-rule or something?
Yeah, well, I have to look at this, you're right. And I just have to note that the high weight satisfies the definition of this. Right. And then it will be this. So the only question is whether this high weight satisfies the appropriate condition. So if I take only one star, this is, we've seen this before, it's minus W0 nu 1. And what do we know? We know that nu 1 is in xt plus intersection what? W u minus lambda. Right? Now, if I take minus this thing, it's going to certainly be dominant again. So let's just write this out. So this is going to, so nu 1 minus nu 1, this is certainly inside of xt plus. That's not a problem. You've seen that before. Okay. So now let's look at this. So nu 1 is equal to W times mu minus lambda. Okay. So now I'll hit it by minus W0 nu 1 is what? It's W0 W lambda minus. Right, because I put a minus sign in here, I just switched these two around. Yes? So this is in W of lambda minus m. Always admired people who can like end the proof at the very tip of the ball. Sometimes you kind of get lucky doing this. Okay, well anyway, that finishes the proof right here. There are people who are I've actually heard stories about people whose lectures are sort of timed so that, you know, the last thing that they say is at the very tip of the ball. It's amazing. I don't know how they do it. This is purely luck, by the way. Okay, any questions on this? Okay, now this adjoining this actually is good because it actually extends the X also. So let me mention that too. So remark is the adjoinness can be extended to X. So I have an X die of G of T, so U lambda V prime is equal to isomorphic to X I of G V, and its adjoints is T. All right, so you can kind of see that this might be quite important because, you know, sometimes you want to compute the X between two of these things. But then you may know some information when I like sort of move things over. So I can actually move this over and say that X to V prime is just, I can just move it over and just take the composition of these two translation functions. Okay, questions on this? All right, so now we are going to get into some, I guess, well, I'm not going to say heavy computation, but these are things that are kind of technical, but they're going to be needed because what we're going to do is we're going to look at, basically going to look at the following questions. So I want to actually like look at blocks which are going to be the same, i.e., you know, the Morita equivalent. So if I take two weights, lambda and mu, which are in the like interior over here, I want to show that this block for lambda is Morita equivalent to the block for mu. Or if, you know, lambda and mu are on the same facet over here, I want to show they're also Morita equivalent. Now, the way we're going to do this is we're going to use the translation functors in order to prove that. So what we actually need to know is what happens to the character of a G module under translation. Now, you might think, well, it's a horrible thing to try to compute, but it turns out that it's not so bad, especially if you're just going to a codimension 1 wall. So if you're going to a wall that has codimension 1, it's not so bad saying what happens from here to here. And in many cases, even coming off the wall, you can actually say something too. Reasonable. Okay. All right, so let's start in. So I have to give you some preliminaries first. These are kind of old computations, but I just want to remind you of them. So let's see. All right, so let's look at these preliminaries. Okay, so first of all, I have to recall this fact. So if lambda is a weight, and we had this sum, let's call it a mu, e to the mu. Maybe I'll just do it this way. So this part is the character part, okay? This is just a coefficient. So this is in invariance. This formal sum is invariant every reaction of. So suppose you have this being true, then when I take the Euler characteristic and if I apply it to this formal sum, I can sort of interchange the Euler characteristic with E here and get something. So actually I can combine it. That's a better way to say it. Combine the two. So AU pi lambda plus. So we actually prove this or observe this a little bit. Okay, so this is a fact that we had before. Okay, now we also had something else. So let me just put this as a dot point too. So suppose I have the character of a module M, tensor module M. So this is the character of M times the character of E. The character of M. And the character of V, we know we can write out as a WP AW of chi W naught. Okay, so V is a G module. So we can sort of write this as the character in terms of simple modules. But then with simple modules, we can write them in terms of the Euler characteristic. And so that's why we can do this. All right. And this turns out to be, what does the character look like? It looks like this. U and x of t of dimension of the mu, e to the mu, because that's just a character now, and then times. So when you expand it out, you can actually write it in this form. All right, so these are sort of two facts. So basically, if you have a W invariant sort of element inside of Z of xt, and you multiply times the Euler characteristic, then you could do some, you can actually combine these two in some sense. And this is just the character of the tensor product, sort of written out in a more gruesome way. Okay. All right, so now I want to actually write a proposition out. And the idea is that I want to write, so this is kind of a, so let me say it this way. So ultimately, I want to take a module and I want to write out the character of the translated module. But in order to do that, I need sort of, it comes in various steps. So I basically have to take the tensor product first and then project. And so I need to actually say what the character of this module is sort of first. So that's what we're going to do. That's what this proposition is all about. All right, so here we go. So let B be a finite dimensional G module with PR of lambda B equal to B. Okay, so I'm assuming that all the composition factors are linked to lambda. So if we do this, we can write the character like this again. So this is sum over W in the affine Weil group is AWs, and because all the composition factors are linked, we can actually do this. I should probably say that here you need that PR lambda. You need this assumption to be able to do this. Okay, so let's write this. This is going to be chi of W dot. Let's be careful. Yeah, you can do this. All right. So what do we know? And we know that AW is an integer, positive, and almost all AWs are all the finite dimensional. All right, so now what we have to do is we have to sort of say what happens with the tensor product. So in the character of M tensor, character of PR of U, M tensor V, is that equal to, so now I got to write a sum again. It's W and W P of AW sum of new dimension of M U, and then chi of W dot lambda plus new. I can do a good job this time. I hope you can see this is a dot over here. This is lambda plus new, where the sum is taken over. On new and exit T with lambda plus u in WP dot E. Okay, so the last condition kind of makes sense because we're projecting onto the mu block, right? So all our Euler characteristics better be, kind of in the right place. Okay, so let's verify this using our preliminaries here. Just kind of putting everything together. So let's do this. Okay, so proof. Okay, so first of all, we just look at the character of this thing over here. All right, so we're just going to use this formula right off the bat. So basically I can write this out as summation of W and WP of AW, summation over nu of the dimension of M nu, and then chi of what? Okay, so let's see, what do I get? I get W. So, oh, I see what we did. All right, so let me write this out and then explain. Okay, so W dot lambda plus E. All right. Okay, so I have to kind of explain what I'm doing. Okay, so first of all, you have from here, you have this. You see that? But then note that now I'm going to use this thing up here. So I'm going to combine this thing in with the sum over here and just sum up over nu plus W dot lambda. Okay, so you're using these two in order to actually say this. Okay, so let's call this 1 and 2. So this is by using 1 and 2. Good. I had to do the preliminaries for something. All right. You don't get things for free around here. All right, so let's keep going. All right, so now what I need to do is I need to transform things. It almost looks like this over here. But I have to transform it in this form over like this. Right? So I have W dot lambda plus nu, and I want to take W dot lambda plus. All right, so let's compare those two. So note the following, and if I take W dot lambda plus nu, this turns out to be equal to W dot lambda plus W1 nu. W1 is equal to W inverse. Okay. And the reason is because the dot action, so the ordinary action, and we could actually show this, the ordinary action is a linear action. So if I take W on two things like mu1 and mu2, it's just W mu1 and W mu2. Now, when you take the dot action, it's the dot action on the first thing and the linear action on the second. That's what the formula is. So I don't know, maybe we should, I'm writing on space here. No. Okay, I think we're done with this. I can erase this now. So we've used this part. So it's a little exercise, but let's maybe do this just to make sure. Okay, so I suppose I think W got two weights, mu1 and mu2. Okay, the dot action. So this is going to be equal to W mu1 plus mu2 plus rho minus rho. Okay. Now this action is linear, so this is going to be W mu1 plus rho minus rho plus W on mu1, mu2. Okay. So then you just formula. This is W dot mu1 plus W ordinary action on mu2. Okay, does everyone see this now? Okay, so the dot action is not linear. Okay, you have to take the dot action on the first thing and the sort of regular action on the second thing. Okay. So right here, you're just taking the dot action on the first thing And then the regular action on the second thing, so W1 is W inverse, let's cancel out. Just kidding. Okay, is that clear now? Okay, great. So now you can see we can just replace this, and that's what we got. So right, so now we just replace. So we can replace because we're summing up all overall news. Right, it's the same thing as summing up all overall W1 news. Right, so then we get that the character, of M tensor this is the summation of all W and WP, AW, sum, all of the new, dimension of M new, and then, let's see, pi of W dot lambda plus. I got it. Okay, good. Now, how do you get this result down on the bottom? Well, I haven't projected yet. So when I project, I can limit the number of things in here. So that in order to get something in here, I need this to be linked to me. So if I take projection on this, so now I'm taking projections. So blah. Okay. So if you get the character of the projected thing, right? Of M tensor U. You just take chi of W plus nu, where, of course, the lambda plus nu must be in the WP orbit. Oh, mu, sorry. Okay, any questions on this? Okay. All right. So next time, what I'm going to do is I'm going to stay at a technical level. So let me just kind of preview next time. So right now we're doing the hard work. All right? I mean, you don't get. I mean, in order to do this, we have to kind of go through a lot of the computations that Janssen actually did. And so the idea is that one can write character P lambda mu of the given character. Okay. And what's going to come into play here is the stabilizer of the affine Weil group acting on the weights lambda and mu. So the stabilizers will be quite important in this game. And so when you're on a codimension one wall, so let's say my lambda here is on a wall, then there's only the stabilizer only has, well, it's an A2 basically. It's just the thing which fixes this hyperplane. Yeah. And so then the number of things in the stabilizer is fairly small, and then you can actually give a more explicit description of this. If you're on like non-codimensional one hyperplanes, then this becomes quite complicated. Okay, but you can actually build things up from codimensional one hyperplanes. So now we're starting to get into the actual alcove geometry involving these translation functors. Okay, let me stop here. No?